Okay, hello everyone. So this is the next in the series of Physics 121 videos. What I want to do today is I want to do an example of calculating magnetic flux first off. So at the end of the last video, we wrote down the expression for magnetic flux, and I've repeated that expression here. So it's the integral of B dot dA, where the integral is over the area of some kind of loop. So we might imagine that we've got some kind of loop. It might be a loop of wire, perhaps, and there is some kind of magnetic field in the region of space surrounding this loop. And what we're going to do is we're going to calculate the integral of B dot dA, where remember the dA vector was an area vector that points perpendicular to the loop, and the magnitude of that dA vector is that little patch of area, an infinitesimal patch of area. And when we take the dot product between B and dA, what we have to do is we have to consider the angle theta that is between the dA vector, or the vector perpendicular to the loop, and the direction of the magnetic field. Okay, so magnetic flux is no different than electric flux, which we use for Gauss's law, except for that we're considering a magnetic field rather than an electric field. So let's just try an example. And in this example, what we're going to do is we're going to find the magnetic flux through a rectangular loop that sits next to a wire carrying a current that is next to a long current carrying wire. Okay, so let's start with a picture. So we'll start with our long wire. And let's imagine that there's a current that is directed towards the top of the screen. So by the right-hand rule, if we put our thumb in the direction of the current, our fingers curl in the direction of the magnetic field, so that in the plane of the screen, what we have is a magnetic field coming out of the screen to the left of the wire, and to the right of the wire, we've got a magnetic field going into the screen. And I'll draw a few more of these magnetic field lines going into the screen on the right. And we'll note that the magnetic field gets weaker as we move away from the wire, if we recall. And so I'll make the spacing between the field lines get bigger as we move further away from the wire. And so these circles with dots and circles with crosses indicate the magnetic field due to the wire. Okay, so of course we know that what the magnetic field's actually doing is it's looping around our wire, but I've drawn just what the direction of the field lines are in the plane of the page. Okay, and then we're going to have a loop that is next to this wire, and so let's draw this loop. Maybe it looks something like this. So it's a rectangular loop, and let's indicate a coordinate system. So this is going to be an x-axis, and what we'll say is that the loop is its left edge is a distance a away from the wire, and its right edge is let's say, a distance b away from the wire. So x equals a and x equals b. And then let's also give our wire some kind of dimension in the vertical direction, so we'll say it's L. Okay, so let's just recall a few things. We could go back and we could use Ampere's law to calculate the magnetic field due to our long wire, or our long current. And if we did that, we could determine the magnetic field due to the current I. And I mean, that would be just repeating a problem that we already did in a previous video. And what we would find is B would have a magnitude of mu naught I divided by 2 pi x, where x is the distance measured from the wire. So over here at the wire is x equals 0. Okay, so one thing we should make note of then is that B is not uniform over our loop area. Okay, so over at the left edge of our loop, the magnetic field is stronger than it is over at the right edge, where x equals b. Okay, so what we want to do is we want to say, if we're calculating magnetic flux, the general expression is the integral over the area of our loop of b dot dA. And so let's just indicate dA of our loop, and let's choose, dA has to be perpendicular to our loop. And so we could choose to have dA coming out of the screen, or we could choose to have it going into the screen. Let's make the choice that our dA vector points into the screen. And so in that way, we'll have dA parallel to the magnetic field due to the wire. So we have B is parallel to dA. So therefore, B dot dA is B times dA times the cosine of the angle between those vectors. But if they're parallel, the angle between them is 0, and so this is 1. And so we have just B dA. So we get rid of the vector part of our integral, which is nice. Okay, and so that's equal to the integral over the area of B dA. Now, in previous problems, what we would have done is, or what we often found, is that the magnetic field, say, was constant, or if it was an electric flux kind of calculation, we'd say the electric field was constant over the surface of some area that we were integrating over. And then we would take that electric field outside. We can't do that in this example. We can't take the magnetic field outside of our integral because, as we've already indicated, B is not uniform. That means that the magnitude of that magnetic field is not a constant. Okay, so what I want to do is I want to go back to this picture and let's try to calculate the magnetic flux, not through the whole loop area, but of just a little section of our loop. So we're going to take a thin strip. And so we'll say that that strip is a distance x away from the wire. And we'll give our strip a thickness dx. And so we imagine that dx is really, really small. And so what we're going to do is we're going to find the magnetic flux, let's say d phi b, through this strip. Okay, and so hopefully we'll find out why that's going to be useful in just a second. So what we could notice first is that the strip is thin, so the entire area of the strip is basically just a distance x away from the wire. And so that means the magnetic field at the position of our strip is just mu naught I over 2 pi x. And so if I wanted to know the flux through that strip, I would multiply that by the area of the strip. And the area of our strip is just equal to the length of the strip, which is L, times the strip width, which is dx. Okay, so what we want to do is we want to say that the flux through this little strip is equal to the magnetic field at position x times the area of the strip, and the area of the strip is just L times dx. Okay, and so what we'll do is for b at x, we're going to use this expression. Okay, so what we're going to do is we're going to say that the flux through the thin, which we've drawn as a green strip, a distance, say x from the wire, is d phi b, which is b at x times dA, and b at x was mu naught I over 2 pi x, okay, and dA was L dx, and so I'm going to write that as mu naught IL over 2 pi, and then it's dx over x. Okay. And so if we wanted to know what would be the total flux, I would just take a whole bunch of these strips and do that same calculation for all of them. The only thing that would change is that the distance x away from the wire would change. And so the flux for each strip is a little bit different, but we just imagine constructing the entire area of our loop with a series of these strips, and then the total flux is just the sum of all those. In terms of calculus, what we would do is we'd say that the total flux is going to be the integral of all of the little infinitesimal pieces of flux, which is going to be the integral of mu naught IL over 2 pi dx over x, and our loop starts at a position x equals a and ends at a position x equals b. Now, we have a bunch of constants. Mu naught is a constant. I doesn't change with, like, I is just the current in our wire, so it doesn't depend on x, our integration variable. L is a constant, 2 pi is a constant, and so what we could do is we could write this as a bunch of constants times the integral from a to b of dx over x. Now, we've done this integral before when we were thinking about, for example, the charging and discharging of a capacitor in an RC circuit. And so remember, the solution is ln of x evaluated between x equals a and b. And so that the magnetic flux is equal to mu naught I over L 2 pi. And then we'd have ln of B minus ln of A when we evaluate between our two limits. But remember the property of lns. The ln of B minus the ln of A is equivalent to the ln of B divided by A. Okay, and so this is the magnetic flux through our loop due to a long straight current. Okay, good. So why did we introduce this idea of magnetic flux? It's because we're going to use it as an essential part of Faraday's law. So we have seen that we get induced currents in closed circuits or loops of wire whenever we change the magnetic flux through the loop. And we found that we could change the magnetic flux in a few different ways. We can have a changing magnetic flux when, well, one example was for emotional EMF, we moved a bar along some conducting rails, and that effectively changed the area of our loop. So we could have the loop area changes. We also imagine taking a magnet and moving it, a permanent magnet, and moving it, say, towards or away from a coil of wire. And so we could change the strength of the magnetic field through our loop. And lastly, what we could do is we could take a loop in, say, a constant magnetic field, and we could change the orientation of that loop relative to the field. So we could, for example, spin the loop. And so we could change the angle between, say, our magnetic field between the magnetic field and a vector that is normal or perpendicular to the loop area. So that's the dA vector in Faraday's, in the magnetic flux expression. Okay, now if we think back to emotional EMF, we said that really what we calculated was this effective voltage, and if our current was propagating in a circuit that had some resistance R, then the induced current had a value determined by the EMF divided by the resistance of the circuit. So an EMF must drive the current, the induced current, and if the circuit has a total resistance R, then the I induced is equal to whatever that induced EMF is divided by the resistance of the circuit. Okay, so what Faraday did is he did a series of careful experiments. So Faraday's careful experiments with magnets and loops of wire showed that the induced EMF occurred whenever the magnetic flux through the loop changed. And so we just listed above the three ways that we could do that. Change in area, change in magnetic field strength, change in the orientation of the loop relative to the magnetic field. Okay, so he did more than that. That's a qualitative observation. He quantified his observations. And so what I mean by that is he actually measured the induced EMF and compared it to calculated changes in flux, and he quantified his observations by showing that the induced EMF was just equal to, it had a magnitude of the time derivative of the magnetic flux. And this is Faraday's law. Okay. So we're calculating just the magnitude of the EMF in this expression. We're not saying anything about the polarity of that EMF. So the direction of, maybe it's better to say, let's say the polarity. So which side is positive and which side is negative. The polarity of this EMF is determined by the direction of I induced required by Lenz's law. And so remember what Lenz's law is that I induced creates a B induced to oppose the change in the flux. So if the flux through the loop was increasing due to some external magnetic field, the induced magnetic field would be in the opposite direction, so as to try to maintain the original flux. If the flux through a loop was decreasing due to some external magnetic field, then the induced field would align with that external field in order to try to sustain the flux that was there. Okay, so we could do a couple examples. Let's do it on a new page. So example. So let's see if we can recalculate some of the motional EMF results. So the picture was that we have some uniform and static magnetic field. So if we have a static magnetic field, that is a magnetic field that's constant, then our induced EMF is not going to be due to a change in the strength of the field. In fact, we know for motional EMF that what we're going to care about is how the area of our loop changes. So we're going to have a conducting bar, as you know, sitting on some conducting rails. And so we have these blue rails, and we're going to say that what we have is some length L here. Sorry. Let's clean this up a little bit. So we have a length L here. And we're going to take this bar and we're going to move it, say, in this direction. So we're going to increase the area of the loop. And we have a magnetic field that points into the page. And let's say that our bar is at some position X instantaneously. And so X will be increasing if we're pulling the bar to the right. Okay, so Faraday's law says we need to calculate an induced EMF as the change in magnetic flux with respect to time. Okay, so to start that, what we have to do is we have to calculate the magnetic flux. Let's say that our loop has a dA vector that points into the screen just like the magnetic field does. So we could say that B is parallel to dA, just like in the previous example. And so that means the magnetic flux is equal to the integral of B dA. This time, the magnetic field strength is constant. B is constant. And so that means that this is B, the integral of dA. And so I just realized that I should really fix my drawing here. What's going to matter is the area of our loop. We're calculating a magnetic flux, and so the length that is relevant is this length. It's not the full length of the bar. Okay, so let's make that fixed. Let's fix that up. Okay, good. So that'll be better. And so because the magnetic field was constant, we pull it outside our integral, and we just get B times the area. So this is the loop area. Okay, so at the instant drawn, we have a rectangular section of loop. It has a height L and it has a width X. And so this loop area is B. Well, the area is L times X, and then the flux is B times L times X. Okay, so this is our magnetic flux expression, and what we're going to do is we're going to use it in here so that when we calculate the induced EMF, it's going to be the derivative with respect to time of BL times X. We said B was going to be constant, and L is the height of the loop, and that's a constant. And so the only thing that changes is the X coordinate, where the bar is, because we're pulling that bar to the right. But dx dt is just the speed. It's the change in position of the bar with respect to time is the velocity. BL times V. And so then the induced current is the EMF divided by the resistance of the loop. And so that's BLV over R. And maybe to be consistent with some previous pictures, what we can do is we can explicitly put in a resistor. And so let's put in a resistor R. And so that R might be a physical resistor, or it might just represent like the resistance of a long thin wire or something like that. And if you compare this to our first calculation of motional EMF, you'll see that this is the same result that we had before. Okay, so let's do another example. This example was an example of a changing area. So changing area. Okay. So in this other example, let's do a rectangular loop of wire next to a long, straight current. Right, we just did this example of calculating the flux for a long, straight current. But what we'll do this time is we'll assume that the current is not constant in time. Okay, so we'll draw the picture. This is basically the same picture that we drew in our first example of a flux calculation, magnetic flux calculation. And so we know that this is now going to be something that changes in time. So let's write our current as some explicit function of time. And so what we're going to have is a current coming out of the screen on the left side, and then we have a current into the screen on the right side. Okay, so this is the same picture we drew at the beginning of the video. Okay, and then we have a loop that sits over here somewhere. And this was a position, this was our x coordinate, remember? And so this was x equals a, and over here we had x was equal to b. All right, so if the current is changing, then we know b is equal to mu naught I over 2 pi x. But now our current is changing with time, so our magnetic field is also changing with time. So we had already worked out some stuff. So we've already worked out that the magnetic flux was equal to, it was mu naught I, and I'm going to put in the time dependence. So I is a function of time, times L divided by 2 pi, and ln B over A. That's what we calculated earlier in the video. So if our current is a function of time, then the flux changes with time. So to go further, we have to make some assumption about the time dependence of the current. So suppose I of t is some exponentially decaying function. So it's some amplitude I naught times e to the minus t over tau. And so if we were to plot that as a function of time, the current would start at t equals 0 at I naught, and then it would decay away with time. Okay, so, and the parameter tau is some characteristic time that determines how quickly that decay of the current is. If we set t equal to tau, then we'd have e to the minus tau over tau, or e to the minus 1. E is about 2.7, so e to the minus 1 is 1 over 2.7. 1 over 3 is a third, so roughly somewhere a third down here, we would end up with a current that is equal to I naught divided by E, and that occurs at a time tau. So if you increase tau, then the current takes a longer time to decay. If you decrease tau, then it decays quickly. Okay, so, I mean, if we just make that assumption for how the current varies with time, then we could just put that into our expression. So we have mu naught, then we would have I naught. So mu naught times I, and I is I naught e to the minus t over tau. And then L, and then we have 2 over pi ln of BA. And so I'm just going to rewrite this where I'm going to reorganize the factors. Let's do mu naught L over 2 pi ln of B over A. Those are all constants. Actually, what I should have done is, let me put my I naught in there as well. And then we have an L. So that all we have left over now is e to the minus t over tau. So this is the, sorry, this is magnetic flux, right? It's not current, it's magnetic flux. Okay, so Verdes Law says that the induced EMF now, in this loop of, this rectangular loop of wire, let's suppose, is equal to the magnitude of the time derivative of this magnetic flux. Okay, so we have a bunch of constants, mu naught, I naught, L over 2 pi, ln B over A, and then we have our time derivative, and our function of time is this exponential decay. Okay, so the derivative of an exponential, like d by dx of e to the x, is just e to the x back. So we're going to get our exponential back, but we don't have just e to the minus t. We have e to the minus t with some constant. And so what we have to do is we have to pull the constant out, right? It's a chain rule thing. So you would take you'd get the exponential, and then you take the time derivative of what's inside the exponential, and d by dt of minus t over tau is minus 1 over tau. Okay, but since that's in an absolute value, we're going to forget about the minus sign, and we'll say that our induced EMF is just equal to mu naught, I naught, L. And let's put our 2 pi in, and then we have a tau in the denominator as well, so I'll put a tau in our denominator. And then we have ln B over A, and we have e to the minus t over tau. So we get an EMF that's also decaying exponentially with time. Okay, and so finally, the induced current we're going to get is the EMF divided by the resistance. And so if we wanted to write all of that out, we'd have mu naught, I naught, L over 2 pi tau. Now we have an R in the denominator, ln B over A, e to the minus t over tau. Okay, so we would get an exponentially decaying induced current. So our induced current decays exponentially. And that occurs just because we assume the magnetic field had an exponential decay, and the induced EMF is a derivative of the magnetic flux. And if B is exponentially decaying, we take that derivative of the exponential and we get that exponential back again. Okay, so we could ask one more question. We could ask, let's just make a note here that R represents the total resistance of our loop of wire. Okay, the one more question we can ask is, what is the direction of I induced? So is it clockwise or counterclockwise? Okay, so what's going to be important for determining this direction is determining whether the flux is increasing or decreasing. So we see here that our flux decreases through our loop with time. Okay, so it starts large and it eventually will go to something that's very small. So since the magnetic flux through the loop is decreasing with time, Lenz's law says that I induced acts to create a B induced that opposes the decreasing magnetic flux. And so how is it going to oppose that decreasing flux? It's going to establish a B induced that is in the same direction as B. And so we had B into the screen at the position of our loop, and so our B induced is going to be into the screen. So we can go way back to our picture here, and we require that B induced must be into the screen. And so then we ask, well, what is the direction of the current? Well, we could use right-hand rule. By the right-hand rule, we put our thumb of our right hand in the direction of the induced current, induced magnetic field, and curl our fingers around, and our fingers curl in the clockwise direction, and so that means our induced current goes clockwise around our loop. Okay. So by the right-hand rule, B induced requires a clockwise I induced. Okay, good. And so maybe that's where we'll stop this video. I think we have only a couple left, and so we're nearing the end. Okay, so with that, thank you very much, and I will talk to you next time.